So today's lesson, we're going to look at something called the natural logarithm and an important number or constant in math represented by the letter E, small e. So let's look at our objectives. First off, we want to understand where the value of the constant E come from. Why is it significant? And what is it used for in math? And then we'll see that a natural logarithm utilizes that constant value of E as its base. And then we're going to look at one specific example or application of this natural logarithm or the constant E in something called continuously compounded interest formula. All right, so the constant E is an irrational number, meaning it's a decimal that continues on without repeating, similar to pi, and it has a value of approximately 2.7183. Now, where do we use E? We use E as a base in an exponential function that is representing or modeling continuous growth. Now, what do we mean by continuous growth? Well, we'll get to that question in a minute. Let me just put E in the context here of kind of the mathematical hall of fame for numbers, right? It's the top 5 in numbers, right? And what are some of those other numbers? Well, 0, you may think, what is 0 so special about? But it has some unique properties. And it wasn't until fairly late in the evolution of mathematical thinking that the concept of 0 even existed. So we have 0, we have 1, also has some unique properties. We, of course, have pi. We have I, the imaginary number. It stands for the square root of -1. And to that, we're going to add this number called E. It's called Euler's number. It's based on a mathematician who helped develop this concept. All right. Now, we said it's used to model growth that happens on a continuous basis. So the first thing I'm going to do is create a contrast here between what is something that has continuous growth versus discrete growth. Now, pretty much everything that we've worked on so far has been an example of discrete growth. Think of the example we had back at the beginning of the unit, right, about bacteria, that they triple their population every day, and we have a starting population of 1. Right? So here's how we model that. Y equals 1 times 3 to the x. And we could figure out what the values are as the population increases with each day. Now, when we graph those, we put dots, right, on the graph, and then we would fit a nice smooth exponential curve to that. But the reality is these bacteria are not just going to instantly appear on a continuous basis, right? Or if most animals, when they reproduce, nothing happens for a while, and all of a sudden, boom, they reproduce, they have offspring. So if we plotted those values, the way the value would actually behave in between these periods would be, it would reach a new level and then stay constant at that for the remainder of that time period, right? And then do the same thing between day 1 and day 2, between day 2 and day 3, and then day 3 we see the increase, and then it remains constant for a while, and then we see the increase, remains constant for a while. So this is what we would call discrete growth. It grows on kind of a step-by-step basis, right? Based on our growth factor, how much larger will it get each time period. So this is an example of discrete growth. Now, if we were to try and model it as continuous growth, let's see what that looks like. Okay, but discrete growth, we're going to say occurs in steps, and we can see the change after a specific event or time period. Now, what if we started with 1,000,000 bacteria, right? Would all the bacteria reproduce at the same time interval? No, they're going to be randomly producing continuously, right? There's got to be at least a few of those 1,000,000 bacteria at any instant, right, that are going to be reproducing or replicating themselves. So here, the graph would have a nice smooth shape to it, because we really truly would have a continuous growth. At any instant in time, we're going to have bacteria that are increasing. So with continuous growth, change is always happening. We cannot point to a specific event or time at which the change occurred. So that's the difference between discrete growth and continuous growth. So here's an example of how we would model that if we had a starting population of 1,000,000. And notice what we're using for our base. We're using this value of E for continuous growth. So here's just in summary, kind of a graphical picture that helps us to contrast the difference here, right? Discrete growth happens where we have an event, whatever our time period is, and then kind of a stepwise increase. Continuous growth, we're going to model using this base value of E, 2.7183. So since we could use E as our base, we can also use it and write it in a logarithm, right? So if we have a log that uses E as its base, we're going to call that the natural logarithm. Okay, so natural logarithm is a log that has E as its base. Now, the way we're going to note that, we could write out log and then put the little e underneath it, but we can also just write ln. Now, this looks like an I or a 1, but it's actually a small l, lowercase l. So ln, logarithm natural, is where that comes from. So when we see ln, what it's telling us is we have a logarithm that's using this e value, 2.7 ... as its base. And if you look on your calculator, right, remember we said the only log that your calculator can take is a common log? Well, I kind of lied to you a little bit, because right next to the common log key, you'll see a ln key. So the other type of logarithm that our calculator will compute for us is a natural log. All right, so we can write this as a exponential function, right? In exponential form, y equals e to the x. What would the graph of that look like? Now, this goes back a few lessons here, but remember when we wanted to graph an exponential function or sketch it, we could do it by simply putting 2 points in. You remember what those 2 points are? The first is, what if we put in 0 for x? Any base raised to the 0 power is 1. So we have that same point, 0, 1, on the y-axis. What if we put in 1? We'll try it. You'll also find a function on your calculator that says e to the x. So if we raise e to the first power, we basically get the value of e, 2.7183. Again, it's an irrational number that goes on, but 4 decimal places is fine. So that would be that value. And then if we raised e to the second power, we would get this 7.3891. So we could sketch in what that looks like, right? What the graph of the exponential function y equals e to the x looks like. So just take a second, find your calculator and see if you can compute these values, e to the 4th, e to the -3, and e to the 1/2. Okay, so pause the video, figure out your numbers, and then see if you got what I got. Okay, here we go. E to the 4th, 54.5981. E to the -3, we get a decimal less than 1, 0.0498. And e to the 1/2, we get 1.6487. Okay, so it's important you're able to take e and raise it to any power on your calculator. All right, we can also use our calculator to evaluate natural logarithms. So look on your calculator, find that ln function key should be very near the log key. And let's just try a couple examples here. So natural log of 20. Remember, what we're really asking is e raised to what power gives us 20? And if you let your calculator do that, you should get 2.9957. Here's another one, natural log of 1. Go ahead and do that on your calculator. So e to what power gives us 1? Well, anything raised to the 0 power, right, gives us 1. How about natural log of e, the e value itself? So remember, what we're asking is e to what power gives us e? Well, the answer would be 1. And here's what it looks like in exponential form. So that last one, natural log of e equals 1, that's kind of an important little identity here. So remember that. We're going to use that here in just a minute when we're trying to solve equations with natural logs. So remember those three properties of logarithms: product, quotient, power property. They all work with natural logarithms too, right? It doesn't matter what base it is. So if we want to ask you to simplify this logarithm that has natural logarithms into a single one, what would it look like? Well, we could use the power property, right, to move the 3 back as the exponent. And then we can use the quotient property to write this as a single logarithm. Now, 4 to the third divided by 8, can we simplify that? Yes, we can. It'd be 64 divided by 8, or natural log of 8. All right, let's have you try a couple of these just on scratch paper. So natural log of 2 plus natural log of 4, we're going to use the product property and multiply those two, natural log of 8. Natural log of 5 plus natural log of x. Well, we have a variable, so all we can do is just multiply them. Natural log of 12 minus natural log of 6. We're going to use the quotient property. So we would have natural log of 12 divided by 6. We can simplify that, right? We get natural log of 2. And one more, natural log of x minus natural log of y. So again, quotient property, and we're just going to leave it as natural log of x divided by y. Now, we can also use those same properties to expand natural logarithms. So how would we apply the properties to go from 1 logarithm to, in this case, 3, right? We've got a factor of 4 and x to the third in the top. That would give us 2 logarithms. And we're dividing by y. That's going to give us a third one. So we can first split them into the 3 logs, natural log of 4 plus natural log of x cubed minus, because we're dividing by y, the natural log of y. And then the last step, let's take that exponent of 3 and move it to the front. All right, let's have you try a couple of these, expanding. This is good review, right, of using properties of logarithms. So natural log of x divided by y. Okay, here we go. We're going to use quotient property. So we can split this into 2 logarithms. Natural log of x minus natural log of y. How many logarithms here? Well, we have natural log of 3 times r to the 4th. So we're going to have the product property will give us 2. Now we're expanding, so we want to take that 4 and move it to the front. So there's our final answer. All right, let's try a couple more. Natural log of 6 over 11 raised to the 5th power. All right, so we have natural log of 6 to the 5th minus natural log of 11 to the 5th, right? That 5 exponent applies to both 6 and 11. So now let's just move that to the front. Nothing we can do to simplify there. So there's our final expanded logarithm. And one more. How many logs? We have 7 m to the 4th and n squared. So we're going to have 3 logarithms. And then the exponent of 4, we're going to move to the front using the power property. Okay, so nothing really new here. I'm just showing you that all the things that we've learned how to do with logarithms of any base, including common log, can also be applied to natural logs. All right, how do we solve equations? So let's take this logarithmic equation that's using natural log. So natural log of 5x equals 3. Same strategy, right? How do we solve a logarithmic equation? We write it in exponential form. But remember, our base now is e. So we would say 5x equals e to the third. Well, e is just a number, right? 2.71 ... So use your calculator. What is e to the third? We find that that's 20.855. We divide by 5, and we get our answer of 4.0178. So same method for solving natural logarithms. Write it in exponential form, but use our base of e. How about if we have a logarithmic equation? Oh, actually, another example here. Let's rewrite this in exponential form, right? So we have e to the eighth equals 2m plus 3. Now, e to the eighth is going to be a pretty big number, but let's go ahead and do that on our calculator, 2,981. So we're going to subtract 3 and then divide by 2, and we get our answer of 1,489 for our unknown m. Now, exponential equation, how do we solve these? Remember, we took the common log of both sides of the equation. So we could do that, but the more eloquent solution here is to take the natural log of both sides of the equation when we have a base of e. And you'll see why that is really helps to simplify things quickly here in a minute. So let's go ahead and do that. We'll take natural log of e to the x plus 1 and natural log of 30. So we use the power property, right, to move the exponent x plus 1 to the front. And then we need to solve for x. Now, here's where things start to get simple quickly. The natural log of e, remember I told you to remember that from a few slides ago, the natural log of e is always going to equal to 1, right? Because e to the first power gives us e. So we can just replace that natural log of e as 1, which basically means we can kind of forget about it in our equation. Now we're left with x plus 1 equals natural log of 30. So we'll use our calculator to find the natural log of 30, and we get our final answer, 2.401. All right, let's see if you can solve this one, same way. Okay, here we go. First thing we're going to do is divide by 7 to get the exponent and its base by itself. Then take the natural log of both sides. Going to move the 2x to the front. Natural log of e is 1. So we're left with 2x equals the natural log of 3. So just natural log of 3 divided by 2. And if we do that on our calculator, we get 0.5493. All right, one application here of continuous growth. It's something called continuously compounded interest formula. So this is an example where you might put money into the bank, and banks pay interest on different time periods, right? They might calculate and pay your interest on a monthly basis. They might do it on an annual basis. They might do it on a daily basis. The standard for savings accounts or loans that you might be paying back is that they typically calculate the total interest on a monthly basis. But what if they paid interest on a continuous basis? This is the formula that tells us how much money we would earn over a certain period of time. And we sometimes call this the PERT formula, P-E-R-T, right? It helps you to kind of remember this formula. So what does all this stand for here, right? Let's look at it. A is for the amount in the account at the end of the period. P is the principal or the starting amount of money that we put into the account to begin with. R is the annual interest rate in decimal form. And T is the number of years, number of time periods that we are wanting to calculate continued growth rate. So if the interest rate is an annual rate, then we want to use years as our unit of measure. And if the interest rate were monthly, then we might want to use number of months as our time period. Those should be consistent. All right, so let's look at an example. Find the amount in your account after 5 years if you deposit $1,050 and earn an annual interest rate of 5%. So let's figure out what we know. We know the principal. We know the interest rate. Now, when we put the interest rate into the formula, we want to enter it in as a decimal. So if we're given in percent, we want to divide by 100. So our interest rate we're going to use in the formula is 0.05. The time in years, we know that it's 5 years. And now we're ready to put it into our formula. So we're going to put all those values in. And now the rest is really kind of a calculator exercise of how to do this in the calculator and get our total amount. Okay, so we begin simplifying this by multiplying what's in our exponent. So 0.05 times 5 gives us 0.25. And then Let's raise e to the 0.25 power first, and then multiply by our 1,050. So at the end of 5 years, our $1,050 would have grown to $1,348 and a few cents, 22 cents. All right, so let's use the formula again, but this time a little different question. We want to have $10,000 at the end of 6 years. How much should we put into an account that earns 4%? Okay, so we're having to solve for our principal, the p-value. So let's put that together in our equation and figure out how we could solve for that. So we're going to solve for p. Now I'm going to do this before we put in the numbers here. So if we want to get p by itself, right, we just want to divide both sides by e raised to the RT power. So that's what I'm showing here. Now let's put in our values, and the rest is calculator work, right? So 10,000 divided by, so let's multiply the exponents first, 0.04 times 6, and then raise e by that power. We get 10,000 divided by 1.2712. And then we find out in order to have $10,000 at the end of 6 years, we would need to put $7,866 in the account today. All right, one more example. Tells us our deposit, tells us how much we have after 5 years. What is the interest rate that we're earning or being paid? So we know the principal, we don't know the interest rate, we know the time, and we know the amount. So let's put all that into our equation. So now we need to solve for r, right? This is an exponential equation. We have a variable in the exponent. So we're going to use the normal steps, right? The first is isolate the base and its exponent. So we want to divide by 1,000. And then we're ready to take the log of both sides. But because our base is e, we're going to take the natural log of both sides. So how do we get rid of the exponent inside the logarithm? We use product property, move it to the front, so that r times 5 or 5r becomes our coefficient. Remember, the natural log of e is equal to 1, right? We're going to replace that with 1. So now it's just using our calculator to say, what is the natural log of 1.4918? And then divide that by 5. And we get our result, 0.08. Now remember, what are we solving for? We're solving for the interest rate. That's the decimal form. So 0.08 would be 8% interest. All right, so that's it. Natural logarithms, we know what a natural log is. It's a log that uses e as its base. E is a number that models continuous growth rather than discrete growth. And we know how to apply that to solve problems like continuously compounded interest. And we realize that all the properties and the ways we have of solving equations work the same way, whether it's a common log or natural log or any other logarithm with a unique base. All right, that's it. Look for the assignment in Google Classroom.